I think we have Luigi Ferrucci waiting for us. Hey, Luigi.
Hi,
How are you doing?
I'm doing very well, thank you.
I'm really happy to have you here. Luigi Ferrucci is the scientific director of the National Institute on Aging, my former boss's boss, I guess, to some extent. Whenever you're ready, Luigi, you can share your screen and begin your presentation. Thank you so much.
Thank you so much. Such an honor to be presenting in this really extraordinary meeting. I was only able to look at some spotty presentation, but what I was able to see was really a cadre of presentation that outline how important is the study of aging and how it's becoming one of the main wave in science. And I think that this is also happening because we all perceive that this work can have a very strong impact on how we are handling our healthcare system for the care of the elderly and people with multiple complex disease. Today, I'm going to talk to you about something that is very, very close to my heart, which is the importance of doing longitudinal study. My predecessor, Nathan Schock, will have agreed with me that outside longitudinal study, we can't really understand the mechanism of aging. And I'm trying to summarize this idea by looking at three hypothetical patients, and this is the timeline, and these are diseases that for a long period of time, they remain subclinical, and then at some point, one of them emerge at the clinical observation. And we call that time disease-free life expectancy, but we know that underneath that clinical definition, there is accumulation of pathology. And the accumulation of pathology now is emerging from the literature occur in a homogeneous and consistent way. So all the diseases tend to have a rate of progression that is strongly correlated, which means that even if we eliminate the osteoarthritis, as they used to say in epidemiology 20 years ago, another disease will come up later on, and then another one, and then another one, and comorbidity and multimorbidity is really the hallmarks of clinical hallmarks of aging. And you can see that, what we really need to do is to create a patient and push patient in this situation where we intervene so that instead of targeting one disease, we target all of them, and we try to delay all of them so the disease-free life expectancy is expanded and the good life become a larger percentage of the human life. And also, we want to detect the individual that tend to have this deterioration accelerated so that they show manifestation of multiple disease earlier in life than the general population. So what I'm saying is that instead of targeting single disease, we should do something that is much more focused. And instead of using specific disease prevention that we are discovering, really targeting multiple disease, we need to find a way to slow down aging. And by slowing down aging, not only we will avoid the multiple disease, and we will delay this disease and have also an impact on longevity, although in my view, that is a side product. We expanding the length of life is great, but if I have to make a choice, for me, health expectancy is really the target that we need to do. But can we slow down aging? And even before that, can we measure the rate of aging? If we can't really measure the rate of aging, how do we know that we can slow down aging? And there is a lot of research that's been done. And when you do something like that, you need to start with an operational definition. So we think that the biology of aging is modifying some of the phenotypes of aging, and these phenotypes of aging are those that are causing the clinically important variable that a geriatrician value the most, which are physical and cognitive decline. However, I will show you today that this is only relevant if we take a longitudinal perspective. First of all, why longitudinal studies are important. For many of you will be clear, but some of you may want to, go a little bit deeper into that. Let's say that I am, examining the difference between four individuals of different age. And so this individual may have the different for a certain parameter, but uh, making the assumption that the only difference between this individual is age, it will be a wrong statement. Why? Because let's say this individual that is now 105, this person was age 20 in 1915. So that means during World War I, this 90 years old was 20 years of age during the Great Depression. And this person was age 20 during the Green Revolution, where really for the first time there was enough food for everybody in America. Not that everybody received that, but there was enough food for everybody. And then this person, age of 20, in 2000, when I wrote this slide, had an unemployment rate dropped to 3.8%, which was really the lowest rate that was registered in the United States. So you can see how these individuals not only are different from their age, but they're very, very different from the experience of their life that clearly affect what they are now. And another important issue is selective mortality or loss to follow-up. So these are the number of chronic disease in the Baltimore longitudinal study of aging measured at the time of entry, and these are the rate of change that were registered in this cohort that were followed over time. As you can see that those lines don't even touch, and the rate of increase is much higher. That is because the unhealthy part of the population either die or lost to follow-up because are much more less likely to come to our study. The only solution for that is to look at longitudinal studies. And that comes to the evaluation of the rate of aging. And I think that the genial discovery of Steve Horvath and Hannum that there is a secret in the methylation of DNA that can be summarized in score that predict chronological age really changed our field. And this was repeated by many others, showing that when you take those parameters of methylation and you compare them with chronological age, the difference between them, it's important metrics of health. In fact, predict mortality and a number of different outcomes. And we can do the same with proteomics. People have tried to do the same with transcriptomics. I would say less successful. But the problem is that all this work was done cross-sectionally. And as I showed you before, cross-sectional analysis may be misleading. For example, let's say that we are using a composite parameter. Here we want to see whether this composite parameter that is made of 6 biomarkers, just for simplicity of the example, you see that they can compare with chronological age, and in some cases, in some individual will be older than expected, some other will be younger than expected, and some other will be older than expected. But the important biomarker that convey this information may be different across different individuals. And in fact, when you calculate and estimate these parameters from cross-sectional studies, you don't know whether this parameter that I'm measuring here cross-sectionally was already that way, at birth or immediately after birth. And so I don't know whether the rate of change of these parameters over time will reflect what we expect from aging. And to give you a very clear example, these are the distribution of slopes of longitudinal change in percent methylation in the Chianti study over 13 years of follow-up. I see 9 years, but that's a mistake, 13-year follow-up. So you can see that many of these slopes of the CPG that were selected for the Horvath model don't change at all. They show absolutely no change over time. There is a small number that show substantial change over time, and those are those that probably convey the information about aging and health. So switching from cross-sectional to longitudinal estimate will probably provide a lot more information. And so, and when you look at, longitudinal trajectory, you can understand a lot more than look at the cross-sectional study. This is a beautiful study done by Susan Resnick on BLSA on the accumulation of beta amyloid by PET in people that were ApoE positive and ApoE negative. But I want to show you here one parameter. Individuals that are below the threshold of 1.2, and they show no longitudinal change over time, very, very little. The individual that at baseline already have or close to the threshold of 1.2 show substantial change over time. But what's really striking here that everybody show exactly the same rate of change, suggesting that this is a disease that determines a switch in biology where, if this was random variability, you will see that each individual will have a different slope, but it's not. And so there is something that is beyond that. These are a classical study showing that if you look at change in aerobic capacity in the population from cross-sectional measure and from longitudinal measure, you make a great differences. And I want to show you something that recently we are developing in the LSA, which is a different way of looking at the phenotypic rate of aging. This is led by my brilliant fellow Perry Kuo. And you see that when you look at a phenotype score, for example, fat mass, you see that over aging, you have a curvilinear trajectory. And so you characterize not cross-sectionally, but longitudinally this individual. And then you can compare single trajectory of single individual to what is happening to the population. And you will see that in this individual, some of them tend to have accelerated change, and some of them tend to have decelerated change. And you can summarize all these phenotypes that are collected longitudinally in the LSA and create a score that show, a very, very wide distribution. So all the parameters of body composition, homeostatic mechanism, energy regulation, neuroplasticity show really large variability across the age range, so that they summarize rate of aging across different domains. And I don't want to show you the final slide, and so I removed that because the paper has been just submitted, and show you that these estimated longitudinal phenotypical trajectory are really incredibly powerful predictor of change over time in physical and cognitive function. So think longitudinally, because your data will be more solid and probably more relevant for human health. And I want to finish by saying one thing really important in this meeting. There is a temporal gap between what happened at the biological, phenotypic, and functional level. Because of compensatory strategy, only above a certain threshold of damage, biological aging will determine change in phenotypic aging, and similarly, phenotypic aging will determine change in functional aging. That means that if we can read biological aging, if we can understand who is aging faster than others, we can capture this phenomenon before this has been translated in phenotypic aging and functional aging. And finally, we understand why we're so little successful in providing, care to people that are frail, because at this point we have lost all the functional reserve at the three biological phenotypic functional aging level. And so we're fighting a really, really strong battle. It's something that, you know, does not have, the resilience necessary so to obtain recovery. I finish here. Thank you for your attention. And again, congratulations for this extraordinary, beautiful meeting.
Thank you so much, Luigi. Really interesting talk. Are there any questions here in the audience? Otherwise, I will start with a question that I wrote in Slack that's also upvoted. So in the PLSA, does methylation age predict morbidity? And which diseases are most associated with change in DNA methylation age?
So in the BLSA, we are just collecting longitudinal data. So I tell you that there is methylation difference according to cardiovascular disease. This seems to be the most important disease signature. But when you look at the longitudinal trajectories in the Baltimore, in the county study where we have longitudinal data, really metabolic disease seems to, take over. The change in insulin resistance, the change in body composition that occur with age seems to capture the longitudinal change in methylation. I think that we see very little longitudinal change in methylation so far from cancer. There seems to be a completely different signature, but I think that of course, there's so little longitudinal data that it's still difficult to know.
Great, thank you very much. We have one more question from Slack. This is Kyrie Wilson, who asks, do you know if anyone has looked at whether individual nitrogen excretion rate versus intake can be used as an aging biomarker?
Oh, I don't know if anybody has looked at that. But I think that, the study of NO, it's rising to the top of interest. I think that, one of the other life I have is to work on peripheral artery disease with Mary McDermott at Northwestern University. And it's becoming clear that the dynamic of enos and release of NO and changing the circulation, and maybe also supplementation with B2s could be really important intervention. So I don't know, but I think that is an extraordinarily important question.
Very good. I think we will stop here. Let's give Luigi another round of applause. Thank you so much for your interesting talk.